Dear students, good evening to all of you. Last class we discussed about problems related to DC machines. In today's class, we will discuss here. If you look at the syllabus, in the DC machines, we have to concentrate on motoring and generating mode of operation and their characteristics. So this part I think we left over that. So just we will go through quickly. Now in sorry. Now in DC machines we have DC generator and DC motor. In DC generators, separately excited DC generator, separately excited DC generator, series wound DC generator, shunt wound DC generator. In this shunt wound, again short shunt wound, short shunt compound, and long shunt compound. So these are the categories of generators we basically refer in DC generators, right? Now, first, if we look at the separately excited DC generator, we know that we have an armature coil here, armature resistance also will be there. We will connect the load. Now this is the generator, and here whatever the voltage or we can say EMF will generate, that is EG. Current flowing through the armature is IA, and here it is the load. Current flowing through the load is IL. So since it is a separately excited DC generator, so the field is separately we are connected to the DC supply. Now this is the field coil, current is flowing through the field coil is IF. In this case, if you look at that, IA is same as I load. V is equals to EG minus IA RA. This is the IA RA is the armature ohmic drop because of the armature resistance. Now, if I try to draw the characteristics for DC generator, we will discuss the DC motors later. Now if we talk about the separately excited DC generator characteristics, basically the characteristics are: one is open circuit characteristics, second one is EG versus IA, third one voltage, terminal voltage versus IA. Now this open circuit characteristics, or we can say no load characteristics, this EG versus IA we can call it as internal characteristics. V versus IA is external characteristics. External characteristics. Now, if you look at that V and EG, V is equals to EG minus IR. So it is, so it will follow the V will follow the EG similar to that, but only there is a difference between the armature ohmic drop. Then how it will how the open circuit characteristic, just I will try to draw the for a DC generator. Basically, if I draw that field current versus generated EMF. So you are exciting the generator with the field. So if we are the field current is increases, automatically generated EMF also increases. So we can say that it is like a linear characteristics. So in practical case, we can draw the waveform like this after the till the saturation period, right? So this is the no load characteristics. So basically, these characteristics are same for all generators, because if the field current increases, automatically generated EMF also will increase. Now, if you look at that EG versus IA and terminal voltage versus IA. Now, if I draw one more graph here, armature current IA, and here it is. Let us take EG comma terminal voltage VT or V. Now here is the rated voltage. So in the DC generators, we have the concept called armature reaction. So due to that armature reaction, what is meant by armature reaction? So we have like the armature is placed at the rotor, which is connected to the brush and commutator setup, and directly we are giving the supply to the rotor. That means, so the current flowing through the rotor will generate some magnetic field. In your stator, there is a electromagnets; those will generate the magnetic field. These two will oppose each other, opposite. So due to that armature magnetic field, it will oppose the main magnetic field. So due to that, the generated voltage EG will slightly will get reduced. You can say that this is the curve. So this is the EG versus IA. Now this gap, we can say that due to the armature reaction drop. Now from this equation, V is equals to EG minus IARA. So we also will follow the same characteristics. Here, this is called uh, IARA, that is armature ohmic drop. Armature ohmic drop. So this is terminal voltage versus IA. So this is called this gap is called due to this gap due to armature reaction, armature reaction. This gap due to armature ohmic drop. So this is how we can draw the characteristics for separately excited DC generator. Now let me talk about series wound DC generator. Now just I will erase all the points. Now series wound DC generator. Series wound DC generator. Now here the generator, we have armature resistance here, and here generator. We are connected one series coil. This is the series resistance, or we can say field coil. We are connected series to the armature. Already here armature will be there. So armature resistance also IA and IARA. Now one more field coil that is connected in series with the armature. So that is current flowing through, that is I series, and we are connected load over here. Load. Now here the voltage developed or EMF generated from the generator is EG. If you look here, the current flowing through is IL. Now IA is same as I series is same as IL. Both all current is same. Now voltage drop. If you look at that voltage drop, this is little more, little higher than the whatever separately excited DC generator, because here it is armature resistance Ra, and here it is one more resistance is existed, that is series resistance. So due to that, we will become E minus I into, so I is nothing but IA, ISC, IL, all are same. So just I will consider it as I into Ra plus RSE. So armature resistance plus series resistance. Now, if you look at that characteristics for the series wound generator, so here field winding is nothing but same ISE. The current is same, that is IA, which is same as ISE, which is same as IL. There is no which is equals to I current. Excuse me. So then generated EMF. As we know that, so by increasing the field current in the sense ISE, if the current field current increases, automatically EG also will increase. This is the like open circuit characteristics. Open circuit characteristics. Now, from the open circuit characteristics, again there is a armature reaction drop. Due to that armature reaction drop, there is a gap between that open circuit characteristics, or we can say no load characteristics, to the internal characteristics, that is EG versus IA, because all currents are same. Now EG V equal to EG minus I into RA into RSC. So again this will become further reduced like this. So this will become terminal voltage. So this gap is due to the armature ohmic drop and the field ohmic drop, both field drop, armature drop and field drop, both the terms armature drop and field drop. So due to these two terms, so the voltage graph will looks like this. This is most of the cases they will see these things. Now shunt wound DC generator. Now shunt wound DC generator. So same as, so here it is generator, armature current is IA. Now we are connecting a shunt field across the armature and generator, so that here it is current is ISH, and here it is we connected the load. So this load is IL, load current. Now previously the currents are all I mean same. Now in this case, here it is the generator voltage EG. Now IA is equals to IL plus ISH. ISH is equals to shunt current ISH is equals to, so what is ISH? Same as the terminal voltage here, and this is like EG minus IARA, right? So ISH is equals to V by RSH, which is same as EG minus IARA divided by RSH. Now what? Okay, so these are the shunt current ISH, right? Now if the shunt current increases, what will happen to the EG? If shunt current increases, EG will increase, and as well as voltage also will increase, right? So now if I draw the characteristics, now here if I take IA, because IA is equals to IL plus ISH, you can say IA or IL, any one you can take, because shunt field is separately, like here separate. Now EG or terminal voltage VT. How the characteristics for shunt wound generator? If you look at that, if IA increases, if IA increases, EG also will increase to maintain the shunt resistance constant, right? So the graph is looks like somewhat like this. This is EG versus IA internal characteristics. Similarly, V is nothing but EG minus IR, Similarly, what we will get here, this is the, we will get here, we will get external characteristics are V versus IA. So these are the three different types of DC generator characteristics. Now we will look at the DC motors. Basically, what are the different types of DC motors? We have series motor, shunt motor, right, and compound motor. What are the characteristics for generator? Open circuit characteristics, internal and external. For motor, we have electrical characteristics and mechanical characteristics. What are electrical characteristics? Torque versus Ia and speed versus Ia. Mechanical means speed versus torque or torque versus speed. So these are the mechanical characteristics and electrical characteristics. Now if I look at the shunt motor, if you look at the shunt motor characteristics, torque versus Ia. In the last class already we discussed, torque is equals to K into phi into Ia. That means torque is directly proportional to Ia. So we can have the linear characteristics between IA versus torque. linear characteristics Linear characteristics, right? Now if I look at the speed versus IA, now IA is directly proportional to phi. Let us take N is directly proportional to EB by phi, or EB is nothing but V minus IA into RA, right? Now if phi value is directly proportional to IA, what will happen? Or we can say V minus IA RA by phi. Now speed increases, so this minus term, or we can say IA increases, speed will reduce. If IA increases, so definitely the speed will reduce. So we can draw the plot for shunt motor IA versus speed, the characteristics like this. And speed and torque, as in the first relation, torque is directly proportional to IA. That means how the IA will vary, that is the linear fashion, it will vary. So if you replace the IA with torque, that is a mechanical characteristics, so it is same as this graph. This is same graph. So mechanical characteristics and electrical characteristics, that is N versus IA and N versus T, both are same, since torque is directly proportional to IA. But in case of series motor, DC series motor, torque is directly proportional to phi into IA. So before the saturation, IA is directly proportional to phi, or we can say IA is approximately equal to phi. So I can write TA is directly proportional to IA square till the saturation. After that, after the saturation, TA will directly proportional to IA. So here two plots we have to merge. What plots now? If you look at that, IA and torque TA, or we can say T. So first it is a linearly, parabolic shape we can observe due to the IA square. After the saturation, so if the core is saturated, then what will happen? Phi is like constant. So then phi is like we can say that torque is directly proportional to IA. That means, so here till now it is like a parabola, and after this it is like a linearly it will vary. This is what the torque versus IA characteristics for DC series motor. Now speed versus IA. Speed versus IA. Similarly, N is directly proportional to EB by phi. So now if we are changing the EB for load currents, small load currents, phi will increase, and as well as IA also increases. So anyway, we know that speed is inversely proportional to phi and IA also. So the graph will looks like this. So now IA versus speed, it is like inversely proportional. Inversely proportional, whenever the current is armature current is minimum, speed will be maximum. So vice versa. That means speed is maximum, armature current is minimum. Speed is minimum, armature current is maximum. Now the DC series motor is like a variable speed motor. If you look at that no load condition, if you look at that no load condition, or we can say light loading condition, the speed is dangerously high value. If you look at that, the speed is dangerously high value, right? Uh, if the if the speed is high, torque will be low. So we will draw the torque versus speed characteristics because it is same as this graph only. So torque versus speed, it is same as this graph. So this one also, if speed is high, torque is low. If speed is low, torque is high. So characteristics of DC series motor. Now we will one more point I want to discuss, that is how to apply the braking for DC machines. Now electrical braking we can apply like three ways. One is dynamic or rheostatic braking. Second one is plugging or counter current braking. Third one is regenerative braking. So dynamic braking in the sense, so first we will armature we will disconnect from the supply and connected across the braking resistance. Now I will try to draw the circuit diagram. So basically if you look at the DC shunt motor, here it is that current is, let us take current is, motor means it's drawing the current IA. Here it is total current I from the supply, and here it is the shunt field winding. Let us take ISH. Now supply. Now if we apply the braking, what will happen? Just we will remove the supply to the armature and we will give the supply to the resistance, braking resistance. So under braking condition, supply is only for shunt field. Series resistance here I can say that. So here it is plus minus supply I series. Now here it is the EB. Now we will apply the braking. Here this is the braking resistance R. So now this is, that means we are applying the, we are increasing the resistance so that it will stop the DC motor. So that braking torque anyway, this TB is equals to 1 by 2 pi into phi Z IA into T by A. This is the just formula just I am writing. Now DC series motor, if you look at the DC series motor, so generally how it looks like. So here it is that EB. armature. So field winding, and here it is the supply. Now what will happen? Just I am giving the supply to the resistor. So here I will give the resistor, and here I will apply the supply to the resistor under braking condition. So this EB terminal, this I will give here. EB terminal I will give to braking resistance. So that means you are connected the complete motor across the braking resistance. So if you are increasing the resistance, so you can control the speed of the motor. So instead of that, plugging. What is meant by plugging? So same thing. Resistance we are adding to the armature directly in series. Now we can say that in parallel we are adding the dynamic resistance. Parallelly we are adding the resistance. Now plugging means we are adding the resistance in series with the armature coil. Now let us take here, it is my uh, shunt field. I just assume here it is the shunt field. So here it is the supply. What happening? So here I am connecting one more resistor. In this place, so this is same field coil. This is RSH, and here I am adding one more resistor. So this resistor causes to control the speed of the motor. So this method we are calling it as plugging. In this case, we are connecting the braking resistance in series with the motor. In previous case, dynamic braking, parallelly we are applying that to that motor, right? Now, and anyway, you already know that regenerative braking. So whenever the back EMF is greater than the supply voltage, we can apply the DC, we can apply the regenerative braking. We are not going to alter any circuit connections, but only the thing is we can apply only for DC shunt motors. But DC series motor, we have to alter the circuit because back EMF is more than the supply voltage for DC series motor. So that special arrangement we have to take care for the DC series motor, right? So these are the different types of tests we have to perform on the DC machines. Now we will look at the induction motors. So in induction motor, operating principle of single phase and three phase induction machine, that is principle of operation, and what are the different types, performance, torque speed characteristics, no load and Brockur rotor test, equivalent circuit, starting and speed control. So in this I already told, from the transformers mostly they will give more marks. Let us take like 6 or 7 marks. From here 4 marks and here 4 marks. And synchronous machines also 4 marks. So most of the times they will give around 20 marks, 15 to 20 marks. So we cannot predict that how many marks from that, but this is the general analysis from the previous year's question papers. Now Just we will look at the numericals based on the induction motors. Before going to that, just we will so the whatever the formulas I used, I taken from the electrical machines by PS Bimra. You can refer, that is very good for electrical machines. Okay, now in DC motors, if you look at the DC motors, whatever the armature coils, we will place at the rotor, and electromagnets we will place at the stator. This armature coils will place at the rotor, and we will give the supply to the armature coils through the brushes and commutator. So directly we are giving the supply directly to the armature in case of DC machines or DC motors. So that's what that machines we are call it as conduction motors. DC motors we are also call it as conduction motors because we are giving the supply directly to the armature. But in case of AC motors, again it similar to the transformer, but only the difference is in the transformer there is no rotating part, no rotational part, but here AC motor there is a rotational part called a rotor. But operation wise, uh, both are like similar because of the magnetic field, because of magnetic flux linking with the stator and rotor will start rotate. So most of the industry, 85% of the industry is depends on the induction motors only, induction machines only. But here the no load current in the AC motor, or we can say induction motor, the no load current, I no load is equals to 30 to 50% of full load current. But in case of transformer, that is very less, 2 to 3% or 2 to 5%. So in case of induction motors, high currents will flow even though the machine under no load condition. So we can say that induction machines more, it has more magnetizing currents. Almost, if you apply the voltage, almost lagging the, like here it is current lagging, current is lagging voltage by up almost 90 degrees. So if it is almost 90 degrees means here you can say, so if it is almost 90 degrees, what is the power factor will be very low. So now we will see that stator and rotor for of a induction motor. Generally stator, which will carry the three-phase windings, either it may be star or delta connected, and it is fed from the three-phase supply if it is a three-phase induction machine motor. And rotor is made up of laminations, same material as stator. Again rotors are again classified into squirrel cage rotor, and face wound rotor, or simply wound rotors. So the theory part you can refer from the textbook. Okay, now the important point of a transformer is like slip. Slip is equals to, we know that ns minus rated speed, synchronous speed minus rated speed by ns. So now we will solve. Okay, now the stator frequency is fs, or we can say f, simply we can say f, stator frequency, and rotor frequency f dash. Then what is the relation between stator frequency to the rotor frequency? Is rotor frequency is equals to slip times stator frequency. Rotor frequency equal to slip times stator frequency. Now, for example, if the rotor is at standstill condition, rotor at standstill condition means nr equal to 0, nr equal to 0, then what will happen? What is the slip? Slip will become 1. Slip equal to 1. So when the rotor at standstill condition, now if rotor is reached to synchronous speed, then what will happen? What will happen to the slip? Slip will become 0, right? So when the, we can say that whenever the speed is varying from no load to synchronous speed, no load to synchronous speed, slip will vary from 1 to 0. This is like speed and here it is slip. Now this is for in case of motor. Now if you look at the generator, rated speed is higher than the synchronous speed. So in that case, the slip is negative. So anyway, that we will discuss in the problems. Now a 3-phase 4-pole self-excited induction generator. Whenever we are talking about the generator, so now what is the slip is ns minus nr by ns. So this is equal to slip. Slip is less than 0 for generator, right? Now if slip is less than 0, ns minus nr also less than 0. So that means ns is less than nr, right? Now from the generator, if you look at that question, induction generator, so we came to this first point. If load is partially removed, the frequency became f2. So previously the frequency is f1. If load is removed, then f2. So then but the speed is maintained constant 1500 rpm in both the cases. So the speed is constant. They're asking how the frequency will vary. For example, in this case they given a 4-pole induction generator. Let us take the frequency is 50 hertz. Now because of like ns equal to 1500 rpm, for pole p equal to 4 and frequency equal to 50 hertz, right? Now what about ns? Ns, sorry, This is like speed is generator is 1500 rpm NR. So NS is less than 1500 rpm. Then if NS is 1000 less than 1500 rpm, then frequency should be whatever F1 or F2, it should be less than 50 hertz, because synchronous speed ns is less than the 1500 rpm because it is a generator. Now f1 and f2 less than 50 hertz, so we got one option. Like option c is uh, like here f1 is less than 50, f2 is greater than 50, this option is not correct. And here both are greater than 50, this is not correct. And f1 is greater than 50, not correct. So the option c is correct, but only one condition we checked. Now if load increases, what about the frequency? If load increases, frequency also will increase. So if load increases, frequency also will increase. That means sorry, if load increases, frequency decreases. Sorry, this, if load increases, frequency will decrease, right? Now previously the frequency is f1. If the load is removed, if load is removed means f2 is greater than f1, f2 is greater than f1. So both conditions are correct, so option c is correct answer. So this time we have like multiple select answers also is there, so that's what we have to be very careful about these conditions. If load increases, frequency reduces. If it is a generator, the slip is negative. Next, leakage flux in an induction motor. So now whenever you are talking about the leakage flux, it may be due to the stator winding or the rotor windings, but not both the windings. Here, flux that leaks through the machine, flux that links both stator and rotor, both they given. So this is absolutely wrong. Flux that links none of the windings, anyway this is wrong. Flux that links with the stator winding or rotor winding, but not both. Because if you if the flux is linked with the stator winding and rotor winding, that will help to rotate the generator, rotor. So that is not a leakage flux. So what is in the leakage flux? Either it may be links with the stator winding or the rotor winding, but not the both. So option D is the correct one. Now the slip of next question. The slip of an induction motor does not depends on. So this is also simple question given in 2012 for 1 mark. Now slip is equals to ns minus nr by ns. So anyway it depends on the ns, it depends on the nr. So option A not correct, option B not, because they given does not depends on. The slip is depends on synchronous speed, depends on rotor speed. But what about the shaft torque? Torque is depends on the speed. If the rotor, the whatever the torque, shaft torque, that is depends on the rotor speed, right? That means if it is depends on the rotor speed, then it depends on the slip. That means slip also depends on the shaft torque, but it is independent of core loss component. Now we can say that the slip of an induction motor normally does not depend on the core loss component. So option D is the correct answer for this question. Now a balanced three-phase voltage is applied to a star connected induction motor, the phase to neutral voltage being V, the stator resistance, rotor resistance refer to the stator leakage reactance, rotor reactance. This is I think XS and here it is XR because of reactance refer to the stator, and magnetizing reactance denoted with XM respectively. Then what about the starting current of the motor? I starting, that is I starting, IS, I starting is equals to now starting current of the induction motor is very high comparatively with the full load current. So starting current is like 5 times higher than the full load current. But exciting current is small. That's why we can neglect the shunt branch, we can neglect the magnetizing reactance. Then what components we will get? So here RS, XS, RR, XR, because in the starting condition the current will be higher than 5 times higher than the full load current. So that's why, so it depends on RS, XS, RR and XR. It is independent of shunt branch. So there is like magnetizing reactance, it doesn't show any effect. So this is not XM, is not, it should not be here, XM is not XM. So option A is correct, or we can say from here. So current I starting, so let us take here, it is the voltage. So I starting is equals to V by RS plus RR plus J into XS plus XR, or you can write V divided by square root of RS plus RR square plus XS plus XR square. Right? Now option A is correct. So simple questions we will solve in this class. In the next class we will solve the some little difficult problems. Right. Now in this question, a three-phase squirrel cage induction motor supplied from a balanced three-phase source drives a mechanical load. The torque speed characteristics of the motor. So we can say torque developed by the motor is Tm, that is solid line, and load line. So here it is torque due to, load torque, we can say that TL of the two equilibrium points A and B. Equilibrium points A and B are given. So which of the following options correctly describes the stability of A and B? So whether A is stable, B is stable, which one we have to identify that? Whether both are unstable, both are stable, we have to find. How to find that stability at a point? Stability at a point means, let us take a pendulum over here. Now, if you take the pendulum up to here, drag the pendulum up to this position, and if you leave that, what will happen? It will move along this direction. First it will take more, then less, and finally it reaches to this position. That means this point is stable at this point. This whatever we are considered. So this is stable at this point. That means if you are creating a small disturbance around this pendulum, either if you drag this side or if you drag this side, now if you are creating any disturbance, what is the reaching point? Let us take, I will give that the pendulum is here, and here. So three different positions are there, which are the stable point. If I ask this question, immediately you can say this is a stable point. How you know that? Because if you move this position like this, it will reach this here only. If I move the drag the pendulum in this direction, it will reach this position. But in case of here, if I drag this one, what will happen? So it will move and again it will go to this position, right? Now this one also it will reach to this position only. That means it is not, if you are creating a disturbance, if you are creating any disturbance at this location, it is not settled down at that point. It is reaching another settling point, right? That's what then only we can call it as unstable. If you are reaching the same settling point, we are call it as stable equilibrium point, right? Now two equilibrium points they given. So here also here it is torque developed by the motor Tm, torque at the load, that is TL. How to find the stable points now? We have to find the acceleration, which direction the acceleration is present. Now let us take acceleration is Tm minus TL, that is the torque developed by the motor minus load torque, that is acceleration torque Ta. Now under the equilibrium point, Tm and TL both are same. Under the point A and point B, Tm and TL both are same. At point A comma B, Tm is same as TL, so Ta equal to 0, because that is the equilibrium points. Now in case of, if we create any disturbance near the point A, now what happens? Now if I choose a point over here, if I choose a point over here, what will happen? Let us take, here it is my point C. Now what will happen at this condition? So this is the TL graph and this is the Tm. So Tm is higher than the TL. Tm is higher than the TL. Tm is greater than TL. Then what about Ta? Ta is greater than 0. So some positive value we will get. So acceleration is positive. Acceleration is positive means it will move towards this direction, right? So that means it will reach point A. So it settles down at point A. So now A is equilibrium and A is a whatever stable point with respect to this point. Now if I take one more point here, now if I take one more point over here, now what will happen? If I take this point, TL is greater than Tm. That means Tm is less than TL. Tm is less than TL. Then what about Ta? Ta is less than 0. Ta acceleration is negative means that is we are called as deacceleration. Acceleration direction is like this. Deacceleration means towards this direction. So it will reach the point A again. So that means A point is stable, because if you create any disturbance of a in the speed reaching the same point, same equilibrium point A, so that then we are call it as A is a stable point. Now same procedure we will apply for point B. Now if I look at this point, what happens? TL is greater than Tm, right? This is TL, TL is greater than Tm. That means Tm less than TL, Ta is less than 0. If Ta is less than 0, what does it mean? It will deaccelerate. Acceleration is along this direction, acceleration. Deacceleration is along the opposite to that acceleration, right? So it will move this path. So it is not reaching the point B. Now if I took a point over here, now if I took a point over here, what will happen? So here Tm is greater than TL, right? In this case, Ta is greater than 0. If Ta is greater than 0, acceleration, that means it will move towards this point, towards this direction. So it is not settling at point B. So we can say that A is stable, but not B is okay, but not B, or we can say B is unstable. So here in the given options, A is stable, B is unstable. Option A is the correct one. Now, yes. Now, if you look at this, the electromagnetic torque TE is same as torque developed at the motor, and it's connected to the load torque TL. Identify the stable points, either A, B, C, D, which are the A, B, C, D, which are the stable points. And here they given the options A, C, D, B, C, B, C, D, A, D. Now, if you look at that, D, okay, we will see one by one. First, we will look at A point. Now, just I'm creating a disturbance in the speed. I'm reducing the speed up to, I'm reaching the speed to this position. So then what I will get at this point, TE is greater than TL. That means TA is equals to TE minus TL. Now TA is greater than 0. If TA is greater than 0, then what will happen? It is like acceleration. Acceleration means towards this direction. So it is reaching point A. If it is reaching point A means it is stable. If you want to check once again, you take one more point over here. At this location, at this point, TL is greater than Tm, or we can say Te. Te is less than Tm, so Ta is less than 0, so it will deaccelerate. Deaccelerate means opposite direction. So acceleration along this path, deacceleration means opposite to that. So this path. Now what will happen? It will reach point A. So we can say that A is stable. If A is stable, so we can ignore this, either A or C. So now we will check whether C is stable or not. It's easy to find the answer, right? Now if you look at that point C, at this, if I create a disturbance here, now the acceleration means this is the acceleration direction, because speed varying, this is the acceleration direction, right? Now if I take this position, if I take this position, TE is greater than TL. That means TA is greater than 0, because TA is equals to TE minus TL. So if it is this is higher, so definitely it is greater than 0. So it will accelerate. Accelerate means towards this, speed will increase towards this direction, and it will reach to point C. And if you look at point over here, if you look at point here, what will happen? TL is greater than TE, or we can say TE is less than TL, then TA is less than 0. If TA is less than 0 means deacceleration. That means deacceleration is towards the C. So again we can say that C is stable point. Now A is stable, C is also stable. So we can easily select that option A is correct. But we will check that the remaining operating points like B and D also. Now the speed is increasing in this path. That means acceleration is towards this direction. Deacceleration is opposite to that acceleration. Now let us take point B. At this position, so TE is greater than TL. If TE is greater than TL, what about TA? TA is greater than 0. If TA is greater than 0, this will get accelerate this direction. If it is accelerating, so it leaves the point B and it is reaching some other point, other settling point somewhere. It is continuously, it is increasing. So now B is not a stable point with respect to this. Now same thing if I apply over in this region. Now in this region, TL is greater than TE. This is TL graph and this is TE graph. So TL is greater than TE. So TA is less than 0. That means deaccelerate. Deaccelerate means this side it will go. So now I don't know, I mean, at where it will get settled, but exactly it won't settle at point B. So B is definitely, it is unstable point. Now we will see that point D also, we will check that. If I create a disturbance like this here, I mean speed, I am varying the speed like speed variation. What is that? Acceleration or deacceleration? Acceleration is this direction, deacceleration is the opposite to that, right? Now I'm considering point D, creating a small disturbance over here. At this point, TL is greater than TE. TL is greater than TE means TA is less than 0. TA is less than 0 means it's deaccelerates. Deaccelerates means this direction. This direction means this direction. So it will reach point D. Right? Now if you look at this position, T is greater than TL. TA is greater than 0. If TA is greater than 0, so it is acceleration is positive, that means along this direction. So that means this direction, it will reach the point D. So point D also stable. If we create a disturbance, it will reaching the whatever equilibrium point, operating point. Now A, C, D are stable except B. B is unstable. Now we will see next problem. Now on the torque speed curve of induction motor, in the figure, 4 points of operation are marked as W, X, Y and Z. Which one of the represents the operation at slip is greater than 1? If slip is greater than 1, now we have three modes of operation. One is slip is positive for motor, slip is negative for generator. In this slip is positive and 0 to 1, it will vary from 0 to 1, but slip is positive and varying from 1 to 2. So in this condition, like braking, so greater than 1 means it is like a braking condition. Speed is negative, but slip is positive, right? Now here it is the speed curve, speed versus torque. Now speed is negative at this point, remaining all our speed is positive only. X, Y, Z speed is positive except W. So speed is negative and slip is greater than 1 to 2 in between. So now this point you can say at W. So option A is the correct option. Now, for an induction motor operating at a slip S, the ratio of gross power output to the air gap power. Now, air gap power is, I will take it is P air gap power PAG, and rotor copper loss, is equals to slip times air gap power, Now, total gross power output, gross power output gross power means air gap power minus losses, that is gross power, no? So air gap power is PAG minus losses is S into PAG, so we can say 1 minus S into PAG. So gross power to the air gap power, so this, let us take PG, gross power. So PG divided by PAG is equals to 1 minus S. So option is B. Next, the direction of rotation of a three-phase induction motor is clockwise when it is supplied with three-phase sinusoidal voltage having phase sequence ABC. For counterclockwise rotation of the motor, this is like a fundamental question for your general class also. You can see that if I want to change the direction of rotation of rotor, what we can do, we can change the phase sequence of any two phases but not all the three. So basically, what are the phase sequence? A B C, A B C, A B C. Let us take now BCA. Here it is BCA in this direction only. So you already know that answer, but just I'm writing. So this is not correct. CAB. So here CAB in this direction only. See, this is also not correct. Then ACB. If you look at this one, ACB, this direction it is there. So it is opposite. That means we can say that two phases are changed. ABC. What I am changing? These two phases I am changing. That is ACB. So option C is the right one. This is also not correct because BC and CAB or CAB. Now, the type of single phase induction motor having highest power factor at full load. So for this question, generally I will tell now voltage lags by current by 90 degrees. So if I want to that's what we are call it as in induction motor, nearly 90 degrees lagging, right? Now if I want to make it unity power factor, we can say getting like more for power factor, we have to add the capacitor, so that I will nearly it will become the phase difference will become reduced, or we can say we can increase the power factor. So for that we will use the capacitor. So one thing I understand, we will use the capacitor. Capacitor start or capacitor run. Capacitor starting means, so at the beginning, or we can say no load condition, or till that starting of the motor, we will use the capacitor, then we will remove that auxiliary winding, or we can say capacitor. So but under full load value, that means it should be run, capacitor should be added to the circuit when the machine is running. So that's what generally I can choose that capacitor run type induction motor for getting power more highest power factor. So the correct option for this one is capacitor run type. Now and because capacitor, if you are capacitor run type, if you are adding, so the machine will work as a like a two-phase induction motor. So then the efficiency also will improve, and as well as the power factor also will get improved. Okay, now if you look at this question, list 1 there is different applications, list 2 has different motors. Now we have to match the list 1 with the list 2, and we have to choose the correct option. Now for the food mixer, we require high speed motors. So high speed motors are universal motors. Cassette tape recorder, anyway, permanent magnet DC motor. And for domestic water pump means single phase induction motor, 3-phase induction motor we will use. For domestic water pump, generally we will prefer single phase induction motor. And escalator we can go with 3-phase induction motor or DC series motor, both you can prefer. Now food mixer 3, cassette is DC motor, that is option C. Option C is the correct answer. Next, starting torque can be obtained in the case of a single phase induction motor with identical main and auxiliary winding by connecting. Now basically if you look at that single phase induction motor, there will be two windings. One is main winding, or we can say running winding, and an auxiliary winding, or we can say starting winding, right? So starting, we are talking about the starting torque. So we have to connect the capacitor with starting winding. What is the starting winding? Auxiliary winding. So capacitor across mains is not correct. Capacitor in series with the machine. A capacitor in series with the auxiliary winding. The main and auxiliary windings are in series. So now a capacitor in series with the auxiliary winding, because auxiliary winding is a starting winding. So option C is the correct answer. Next. in an induction motor, if the air gap increases, what will happen? If air gap increases, leakage flux will increase. Leakage flux will increase. If air gap increases, definitely leakage flux increases. So then what will happen? Then the power factor will get reduced, and even the torque also, breakdown torque also will reduce. Efficiency, it won't improve, speed won't reduce. So then what will happen? Power factor will be lower, breakdown torque will be reduced. So both options are correct. Power factor will be reduced because of more air gap. Now, unbalanced supply voltage given to a three-phase delta connected induction motor will cause, whenever we are talking about the unbalanced supply voltage, unbalanced, if you are observing any unbalanced, so due to that unbalance of the supply voltage, there will be present negative sequence components. So negative sequence components will arise in the system. So option C is correct. Next, skew is used in induction motor in order to reduce torque due to. So what is the mean by like a skew, and when we have to use that in induction motors? If you look at that, number of stator slots equal to the number of rotor slots. Stator, if you look at that, stator slots is equals to rotor slots, right? Now if both are equal, so what will happen? Both teeth are strongly like aligned. They will align that strongly. They will align. We cannot like we cannot rotate the rotor if it is aligned with the stator. So that's why what we will do, we will keep the, I mean, anyway, that phenomena we are called as cogging. So what we will do, we will just rotate the rotor by a small angle. So if you rotate that, what will happen? We will reduce the vibration and noise also. We will reduce, and air gap also we will maintain, because if both are like aligned strongly, so then it won't rotate, it will vibrate. So that is because of slots, or we can say slot harmonics. Now, an 8-pole three-phase 50 Hz induction motor is operating at a speed of 700 rpm. The frequency of the rotor current of the motor in hertz. Now they given, what is the given data? 8 poles, 3-phase 50 Hz supply, and that operating speed is 700 rpm. Then we have to find the synchronous speed. What is synchronous speed formula? Ns equal to 120 f by 3. So 120 into 50 divided by number of poles is 8. Now how much we will get? 120 into 50 by 8. So we will get 750 as a synchronous speed, 750 rpm. Now what is the slip? Slip is equals to ns minus nr by ns So that is 750 minus 700 divided by 750. So 50 by 750. 0, 0, 5 ones, 5, 1, 15. So 515, 1 by 15. Now they are asking the frequency of the rotor current. Rotor current, in the beginning of the class, we discussed about this. Rotor frequency f dash equal to slip times stator frequency. Now slip is 1 by 15. So rotor frequency f dash equal to 1 by 15 into stator frequency is 50 hertz. So we will get 3.33 hertz. Now the frequency is 3.33 hertz. So this is the correct option. Now 1 minute. Now next problem. A 4-pole induction motor supplied by a slightly unbalanced 3-phase 50 Hz source is rotating at 1440 rpm. The electrical frequency in Hz of the inducted negative sequence current in the rotor is how much? So now see, same thing, we have to find the rotor frequency, but here we have to find like synchronous speed ns is equals to 120 into 50 by number of poles is 4, so it will become 1500 rpm. Ns is 1500 rpm. Now what is the slip? S is equals to S is equals to what? How much we'll get? 1500 minus 1440 divided by 1500. We will get 60 divided by 1500. So 6 by 150. um, by 150. So we will get 0.04, or we can say 4%. Now, if you look at that, slightly unbalanced, whenever we are talking about the unbalanced, so negative sequence components are exist. If negative sequence components, what will happen? It will tend to rotate in the opposite direction, right? So that means what will happen? So ns minus of minus nr by ns. So this will become ns plus nr by ns 1 plus nr by ns. So this nr by ns is nothing but 1 minus s, so 2 minus s. So whenever we are talking about the unbalanced supply, so the slip will be 2 minus s because of negative sequence components in the rotor current. Now the slip s dash is equals to 2 minus s, that is 2 minus 0.04. So how much we will get? 1.96. Now I know the slip, I know the frequency. Rotor frequency f dash is equals to s dash into f, 1.96 into 50 hertz. So this will become 1.96 into 50, that will become 98 hertz. Now option B is correct. So in the first question and second question, here it is operating under normal condition. That's what we consider f dash is equals to s into f. But in this case, f dash is equals to 2 minus s into f because of unbalanced supply. Right? Now we will look at that one more question. The block or rotor current in a three-phase star connected 15 kilowatt 4 pole 230 volt 50 hertz induction motor at rated conditions is 50 amperes. So the block rotor current is 50 amperes under these conditions, neglecting the losses and magnetizing current. The approximate block rotor line current drawn. So again they are asking if the rotor current for different voltage and frequency like 230 volt, 236 volts and 57 volts. So the set of readings they given 230 volts and 50 hertz. The current is 50 amperes. Now 230, if the voltage is 236 and 57 hertz, then what is the current? So rotor current anyway I2. I2 is equals to E2 by Z2. Z2 is nothing but square root of R2 square plus X2 square. Now here we are neglecting the losses. Neglecting the losses means resistance we can ignore. In that case, what we will get? E2 by X2. So, but X2 components like inductance and inductance value, we don't have the inductance. But what we have? Frequency we have. So I can write E2 divided by 2 pi FL. Now I can say I2 is directly proportional to E2 by F. So I have the relation between I2, E2 and F. I2, E2 and F. So now I can write here I2 divided by I2 dash is equals to E2 divided by E2 dash into F dash divided by F. E2 by F, F dash by E2 dash, that equal to I2 dash. I2 by I2 dash. Now, what is E2? E2 is, let us take 230. This is E2 230 into f dash. F dash is 57 divided by E2 dash, that is 236, into f is 50. So how much we will get? So 230 into 57 divided by 236 into 50. So we will get 1.111. Now this is I2 divided by I2 dash is equals to 1.111. Now I want I2 dash. I2 dash is equals to I2 by 1.111. So I will write this one as 50 divided by 1.111. So how much I will get? 50 divided by 1.111. So I will get it as 45.00. Now I can say this is option B is correct one. Now in this question, so what is the like data they given? We written over here E2, F2, okay, E2, F and I2, and they are asking to calculate the I2 dash, E2 dash and F dash they given, and they given the clue neglecting the losses. Losses are due to resistance, so we can neglect the resistance. This will become E2 by X2. So X2 anyway inductance they are not given any. Magnetizing current also, that means L also you can neglect or ignore because anyway they are not given in the question. Only it depends, like we have to write the equation I2 is directly proportional to E2 by frequency. So from this relation we can able to calculate the secondary rotor block rotor current when the motor is connected to another set of readings like 236 volts and 57 hertz. Now we'll solve another problem. A three-phase 440 volts squirrel cage induction motor is running at a slip of 5%. The speed of stator magnetic field with respect to rotor magnetic field and speed of rotor with respect to stator magnetic field. So this is a little easy because the speed of stator magnetic field and with respect to rotor magnetic field, whenever we are talking about the magnetic field, so it will rotate and at same speed. Stator magnetic field is same as rotor magnetic field. That means if you are observing from the rotor magnetic field, stator magnetic field looks like it's a stationary because both are will rotate at the same speed. Now we have to see the speed of the rotor with respect to stator magnetic field. This we have to calculate. Now in this question, slip they given 5%. So what is synchronous speed? Ns is equals to 120 F by P. So 120 into 50 by 6 pole machine. So 1000 RPM we will get. Now rotor speed. What is the rotor speed? Rotor speed is 1 minus n times synchronous speed. So that is 1 minus What is the slip they given? S is nothing but 5%, that is 0.05. So 1 minus 0.05 into 1000. So we will get 950 RPM. Now the speed of rotor field with respect to stator, sorry. Now how much we will get? Ns minus Nr. So Ns minus Nr is 1000 minus 950, that is 50 RPM. Now it is in which direction? It is in stator direction, stator field direction. Now as per the question, first one is the speed of the stator magnetic field with respect to the rotor magnetic field is 0 because both will rotate at the same speed. If you look at, both fields are stationary with respect to each other, and the speed of the rotor with respect to stator magnetic field is 50 RPM. Now this is rotor speed 50 RPM. Now speed of rotor with respect to stator. Now speed of the rotor with respect to rotor is 50 RPM. Now the speed of the rotor with respect to stator. So with respect to stator field, what will happen? So this will become Nr minus Ns. So this is 950 minus 1000. So we will get minus 50 RPM. So this is what the answers for that. Now a 230 volts a 230 volts 50 hertz 4 pole single phase induction motor is rotating in the clockwise direction at a speed of 1425 rpm if the rotor resistance at standstill condition is 7.8 ohms, then the effective rotor resistance in the backward branch of the equivalent circuit will be. Now, what is the rotor resistance at stator standstill condition? Rotor resistance at standstill condition 7.8 ohms. Now, what is the synchronous speed? Ns is equals to 120 f by p, that is 120 into 50 divided by 4, so 1500 rpm. Slip S is equals to 1500 minus 1425 divided by 1500 is equals to how much? 1500 minus 1425, that is 75 divided by 1500. So we will get 0.05. Slip is 0.05. Now, if the road in the backward branch, if you look at the question, then the effective rotor resistance in the backward branch, whenever you are talking about the backward branch or backward field, that means negative sequence component. Then what about the slip of rotor? Slip of rotor with respect to backward field, that is 2 minus s. So we will get 2 minus 0.05, we will get 1.95. Now effective rotor resistance. effective rotor resistance, R effective rotor resistance is equals to R2 by 2 into 2 minus S, because with respect to backward branch. Now this will become 7.8 divided by 2 into 1.95. So we will get it as 2 ohms. If I simplify that, I will get 2 ohms. So the option is A. Now we will see the next question. A 400 volts, 50 hertz, 30 HP three-phase induction motor is drawing 50 ampere current at 0.8 power factor lagging. The stator and rotor copper losses are 1.5 kilowatt and 900 watts respectively. The friction and windage losses are 1050 watts and core losses are 1200 watts. The air gap power of the motor will be. So to find the air gap power, first what is the total input power? So we will calculate input power is equals to, for a three-phase induction motor, what is the input power? Root 3 times VI cos phi. Root 3 into voltage is 400, current is 50 amperes, and power factor 0.8. Now how much we will get? So root 3 into 400 into 50 into 0.8, we will get 27.7128 kilowatts. Now air gap power. What is in the air gap power? Air gap power is the power between the stator and the in between the rotor, right? So in between the stator and rotor, so what are the losses will exist? State between the stator and rotor in the air gap, the losses are rotor copper loss and the core losses, or we can say core losses due to stator, core losses due to rotor. So now I can say that losses are, what are the losses? 1.5 kilowatt plus 1200 watts, that is 1.2 kilowatts. So we will get 2.7 kilowatts. Now, so in now air gap power, P air gap power is equals to input power, P input minus losses. 27.7128 minus 2.7. How much we will get? 27.71 minus 2.7. We will get 25.01 kilowatt. So now option C is the correct one. So here now we will look at the next question. An induction motor runs stably under constant torque load at 1250 rpm of a 50 hertz supply. It's a number of poles. So it is like a simple question. So number of poles, how to calculate number of poles? So now as this question, an induction motor runs stably under constant torque load. This is number of poles. So if it is running stably, that means speed is greater than the synchronous speed ns. So what is ns? Ns is equals to 120 into f by p. Now, so p is equals to 120 into 50 divided by 1250 rpm. So 120 into how much we will get? 120 into 50, 6000 divided by 1250. So we will get around 4.8. So we will consider the integer part of the poles. So number of poles is 4, because the speed will be more than 1250. If it is more than, if it is increases, definitely it will decrease. So this fraction we can ignore, and we can go with integer part, that is 4 poles. Next question. A 6 pole 50 hertz induction motor rotating at 1400 rpm is in dash mode. Now, as already told, for an induction motor there are 3 modes, depends on the slip. If slip is positive, motor; slip is negative, generator; positive and higher than 1, then it is like a braking mode. Now for this case, so what is the synchronous speed? ns equal to 120 into f by p. So 120 into 50 divided by number of poles is 6. So 20, so 1000 rpm. Now what is, see, ns is less than the 1400 rpm. So now what is the slip? S is equals to ns minus nr by ns, right? So now 1000 minus 1400 by 1000. Slip is how much we will get? Minus 400 by 1000. Now minus 0.4 we will see. Minus, whenever we are talking about the negative slip, slip is negative, then the machine is working under generating mode, right? So thank you. So these are the few basic problems or basic concepts we discussed from the induction machine or induction motors. So basically in this class I can say this equilibrium point calculation and how the slip will vary, like slip will vary from 0 to 1, right? Now the rotor frequency, that is very important. F dash equal to slip times of f when it is, when the system is under feeding under balanced supply. If it is unbalanced supply, f dash equal to 2 minus s into frequency, supply frequency. So these problems we already solved. Now one more problems we will solve. Simple problems only I will discuss in this class. Now efficiency. Now let us consider the power input to a 415 volts 50 hertz 6 pole 3 phase induction machine running at running at 975 rpm is 40 kilowatt. The stator losses are 1 kilowatt and friction and windage losses are 2 kilowatt. The efficiency of the motor, the efficiency of the motor is dash. So now in order to find the efficiency, we have to find the output value. So power output divided by power input, right? So now power input already we know that 40 kilowatt. So power output we have to find. So how to find power output? Power output is equals to power input minus losses. So what are the losses they given? Stator losses 1 kilowatt and frictional windage losses are 2 kilowatt. And they are not talk about rotor copper losses. Right? So we have to find the rotor copper loss. Rotor copper loss. How to find the copper loss? Rotor copper loss equal to slip times rotor input. Now, what is the slip value? We will calculate now. Slip S is equals to ns minus n by ns. Again, ns is equals to 120 into f value 50 divided by p6, that is 1000 rpm. Now ns is 1000 minus n is 975 by 1000, so we will get 25 by 1000. So 25 divided by 1000 is 0.025, right? Now slip we calculated. So 0.025 into rotor input. What is the rotor input? So total power input minus stator losses. Stator losses are 1 kilowatt they given. So 40 kilowatt minus 1 kilowatt. So we will get 0.025 into 39 kilowatts, 0.975 kilowatt, or we can say 975 watts. This is rotor copper loss. Now we have stator losses, frictional windage losses, and rotor copper losses. Then what is the total losses? Total losses is equals to 1 kilowatt plus 2 kilowatt plus 975. So total 3975 watts, or we can say 3.975 kilowatts. Now total loss we found, right? Now we will calculate the, remember this 3975. Okay, total output. Power output is input minus losses. That is, input is 40 kilowatt minus 3975. How much we will get? So 40 minus 3975. 3.975. We will get 36.025 kilowatts. Then the efficiency. What is the efficiency? Efficiency is output by input, that is 36.025 divided by 40. So now 36.025 divided by 40 is equals to, so 90.0625. So around 90% efficiency we will get into 100. So we will get the efficiency of the induction motor the 90.0625%. So this is how we can calculate the efficiency of the induction motor. Now in this class we discussed a few basic problems. I'm not telling up completely we discussed the problems. Basic problems we covered, that is given in the previous year's gate papers. In the next class we will discuss about 2 marks questions, 2 marks problems a little difficult, and as well as synchronous machines. Okay, so thank you for joining the class. Now you can leave the class. Thank you.